Welcome back to another video about LTSpice. In this video, we will have two parts. The first part of the video would be like another example about the parametric plot of a MOSFET. And the second part of the video, I will introduce the concept of automated component in LTSpice. The automated component editiion will be very helpful in case that we want to simulate a random component and we don't want to draw a symbol, because editiion can help you to automatically generate a symbol to fit the Spice model that you download from the website. But let's first focus on another example about the parametric plot in our case, which is the MOSFET. In the previous video, I talked about like the fundamental of the parametric plot of a diode. So if you haven't watched it, please watch it before you watch this one, because it's just another continuous part of the previous one about the parametric plot. You could see this is part 2. So again, now we want to plot a very familiar plot. We usually study about the MOSFET, which is the drain source voltage against the drain current. So drain source voltage is the voltage difference between the drain at this point and the source at this point. And the drain current is the current going in this direction, because this is the N MOSFET, the N channel MOSFET. That's why we have the current going from the drain to the source this direction. And as you could see, we have 3 cases. The first case, we have the gate source voltage around 3 volt, which is the blue line is the case when the gate source is 3 volt. And the second case is when we have the gate source voltage around 4 volt, which is the red line. And finally, the green line demonstrates the final case where the gate source voltage is 5 volt. So in order to plot this one in LTSpice, we need to pay attention. First, we have the variable on the x-axis. So the variable on the x-axis should be a continuous variable. It should be a continuous variable. But the cases, like the voltage source here, represent cases. So voltage source represents 3 cases. The first case is 3 volt, the second case is 4 volt, and the third case is 5 volt. So it's like a discrete variable. So we have the gate source voltage here described by a parameter, discrete variable. But the drain source voltage will be presented by a pulse, presented by a linear continuously increasing signal. If you don't know what does it mean, like linear increasing signal that we can create it with a pulse, please refer to my previous video. I also put the graph of the signal to demonstrate how does it look like. In this video, we will only continue and plot this one in LTSpice. So one more time, in order to have this plot, as you look in the graph, we can somehow summarize that. We need to have 2 types of variables. The first type is the drain source voltage, which should be a continuous variable. So in our continuous variable, we will utilize the pulse. While for the discrete variable representing the case, for example, like gate source voltage in this one, representing discrete case in the plot, we need to use parameter and the step command. So let's go to the LTSpice. So this is the LTSpice that I prepared beforehand in order to make the demonstration much easier. And it's nothing different from what I demonstrated in the PowerPoint. As you could see, for the drain source voltage, we need to have a continuous variable. That's why I use a signal function in order to have a continuous variable, continuous values. While for the gate source variable, we use a parameter together with the step command. In case you don't understand how to use parameter, how to use step command, or how to do the time domain simulation with trend, or even to understand some function signal for the voltage, please refer to my previous video. And for this one, in order to add a MOSFET, it's pretty easy. For example, right click on your schematic to strap and component, or you could just press F2 on the keyboard and then type in MOSFET, NMOS, and you have this symbol. Click OK. But it's only a symbol. It doesn't have any content, no characteristic for the simulation. In order to specify what kind of MOSFET or NMOSFET you want to use, in this case, move your mouse to the symbol of the device and then right click, pick new MOSFET, and as you could see, I picked the PS89 from Infineon. So I picked this one for the demonstration. You can pick whatever here, but I pick this one for my demonstration for this part and also for the second part of the auto-temerated component in the LTSpice. So feel free to do whatever you want. Let's cancel and delete this one. Now let's simulate, run. Okay, we need to measure. In order to obtain the plot, I put the plot here again. So we have the y-axis, the dependent variable is the drain current. So we want to measure the current going from the drain to the source. Okay, with this symbol, it means we can measure the current, but with this red probe means we measure the voltage. When we look at the plot here, the dependent variable is the current going from the drain to the source. That's why we need to measure the current going from the drain to the source. So as you could see on the y-axis, we have the drain current. However, on the x-axis, it is the time, which is not our case in the plot, because in the plot, the x-axis is the drain source voltage. So how could we do that? Okay, let's determine the name of this one. So the name is VD. Delete this one, change it to VD. In case you don't understand what I'm doing, please refer to my previous video about the parametric plot part 1. I explain everything in detail. Again, this one I only want to focus on the example. So now you could see on our x-axis is the voltage between the drains and the source. That's it. So the demonstration to plot this parametric plot between the drain source voltage and the drain current of the MOSFET. This is the end, because you can obtain the plot here. If you want to see like the plot only of the case where the gate source voltage is 3 volt, you right click on the graph, choose view, select steps, and you choose the step where the gate source voltage is 3. So you see only the graph when the gate source voltage is 3 presents in this case. Okay, now let's move to the second part of our video, which is the automated component in LTSpice. Okay, what does it mean, automated components in LTSpice? So you could see this is the model that we use in built-in LTSpice. But I want to find the model from the manufacturer website. As you could see, this is the manufacturer of the MOSFET, Infineon. So let's go to Infineon website, looking for this device, download that device from the website, and we will simulate that device here and compare between the automated component we downloaded from the website Infineon and the built-in LTSpice of the same device. Open another web browser and then you type in the name of your NMOS, which is PSP89 the manufacturer and SPICE model. We press enter, and of course there's the website from Infineon. That's what we look for. And we want to simulate the model that we download from this website. So we need to go to design support, and we need to download the PSpice. So you see SPICE model. So we click download. We choose a folder where you want to put your, I will put it in download. After you download it, extract it. I mean, if you want to understand more what I'm doing, you can somehow refer to the video that I did before about how to import another third design devices into LTSpice. This one is somehow related to that previous video if you want to understand how to import a third-party device into LTSpice. In this case, we also import a third device from the website, but we will have to do another step, which is like we will automatically generate a component rather than drawing it by hand in LTSpice. So that's the difference. We will use an automatic component generation in LTSpice to have the symbol rather than use a default symbol in LTSpice, because sometimes you don't have a symbol. For example, this is the symbol of the NMOS. Sometimes the symbol doesn't match with the content of the device. For example, let's open this one and we'll see. So this is what we are looking for, right? So Control F, PSP89, looking for that. So now you could see this is the sub-circuit and this is the PS89. This is the model that we are looking for. It has at least like 5 ports. However, if you look at the device here, we have only, for a default symbol of an MOSFET, we have only the drain, the gate, and the source. Only 3 ports. 2 ports are missing. If the symbol doesn't match, in that case we have to draw by hand. However, LTSpice has a function to help us to generate the symbol automatically. How can we do this? First, we will open that file that we download from the website in LTSpice by going to the file, click open, and then you go to the folder where you downloaded. I put it in the download folder in this one. If you don't see anything, please look at here and choose all files and choose the file with the extension of .lib. It is the file containing the sub-circuit of our device. So let's go to the device, Control F, and you will see there will be a searching box here, PSP89, and sub-circuit, yes, this one. You move your mouse to this one and right click, choose create symbol. Do you wish to automatically create a symbol with a sub-circuit PS89 with 5 ports? Yes. So see, LTSpice automatically create this symbol for us, and this is the file. Okay, let's close it. We know that it's already generated. Okay. Now let's add that generated component in our circuit. Right click on the schematic, choose component, and in this box you will look for the auto generated. Double click and you see this is PSP89, which has been generated just a few seconds ago. Choose it, we put it here. Yeah, let's put it here. It seems like the Y doesn't match, so we redraw the wiring a little. So let's compare. I mean the electrical connection of the device that we download from the website has no difference from what we did for the previous example of our MOSFET built in LTSpice. The drain is connected to a voltage source, which is opposed, to simulate a linear increasing voltage, and the gate connected to a discrete variable to demonstrate the cases, the same here, and the source in this case connected to the ground, this one also connected to the ground, so everything is the same. Let's simulate and run. Okay, for the first plot, let's plot our current from the built-in model. This is the current from the built-in model, and we will change it to VD. Okay, let's add another plot. In this case, we will measure the current from the drain to the source of the second one. So this is the model from the drain to the source of the second one, also against the same voltage signal VD. Why do I know that it will be the same? Since if you look at this voltage connected to the drain in this case, which is the VC2, and the voltage connected to the drain in the built-in case is the VC. The content of the signal here and here are the same, so they are totally the same. You could say there will be a very big difference from the built-in model and the model that we download from the website, which is more accurate. Let's look at the datasheet from the website. So this is the design we need to do with the datasheet. So it will be in document. Oh, sorry, my mouse is really lagging. Oh, okay. Document datasheet, and we open in another tab. If we want to compare, we need to go to the plot where it shows in this case. You see the temperature of the environment is 25 degrees, and we also doing the same thing for the simulation here, 25 degrees. And let's look at this. We want to see in the case of 3.6 volt, or maybe, let's see in the case of 3.4 volt, which is this plot, around the drain source voltage of 4, the current of the drain will be almost like saturated at 0.5 ampere. Okay, to have that, we need to change the step parameter to 0.2 and simulate run. We measure it again, and we add another plot. We measure it again for our website model. Good. Now we need to change the x-axis to the drain source voltage. Okay, which is the VD, and we need to choose the graph of 3.4. Yes. So let's touch the cursor. So for 3.4 volt, in this case, need to 4 or 5 volt drain source voltage we will have the current of the drain saturate almost at 0.5 ampere. In our model from the website, this is around like 0.4 ampere. What about the model built-in LTSpice, which is 0.5 ampere? It seems that the model in LTSpice is more accurate compared to the model that we download from the website. I must admit that I haven't carefully analyzed how to connect with the port temperature chain and temperature case, because if I can connect them correctly, it will give better simulation. I hope so, rather compared to the LTSpice built-in model. But I hope that somehow the concept of auto-generated component LTSpice is clear in this demonstration. It might be a failure, but I do learn something, and I hope you guys do learn something too. Thank you so much for watching. See you again.